Witnessing a planet form in real time, spiral patterns around a young star. What are those mysterious swirls surrounding a newborn star? It's fascinating and perhaps a bit awe-inspiring to think that we might actually be observing the birth of a planet in real time. Astronomers have recently made an intriguing discovery. They have observed a developing planet that seems to be carving an elaborate pattern within a disk of gas and dust encircling a youthful star. This startling finding could significantly enhance our understanding of how planetary systems evolve, including our very own solar system. The exoplanet, which is still in its formative stages, is creating a spiral arm pattern in the protoplanetary disk surrounding the star HD 135344b, also known as SAO 206462. This impressive star is only about 10 million years old and resides in the Scorpius OB2-3 star-forming region. While this may not seem exceptionally young, it's important to put it into context. The Sun, for example, is roughly 4.6 billion years old and considered to be in its middle age. This significant discovery was made with the help of the Very Large Telescope, VLT, utilizing its Enhanced Resolution Imager and Spectrograph, ERIS. This event marks what could be the very first instance where astronomers have been able to observe a planet's formation within a protoplanetary disk directly. Francesco Maio, the head researcher from the University of Florence, expressed excitement about this groundbreaking finding, stating, "We will never personally witness Earth's formation, but from 440 light-years away, it appears we may be watching a planet come into existence right before our eyes." According to Maio and his team, this emerging planet is estimated to be about twice the size of Jupiter and orbits its star at a distance comparable to that of Neptune's orbit around the Sun, which is approximately 30 times farther than the Earth is from the Sun. As this potentially new planet navigates through the protoplanetary disk of HD 135344b, it actively accumulates material, aiding in its growth. The infant exoplanet and its accumulation of material. The formation of stars begins in dense regions of vast clouds composed of gas and dust in space, which eventually collapse under their own gravitational pull. As stars develop, they form swirling disks of gas and dust, known as protoplanetary disks, around them. It is within these disks that planets come to life. When planets begin to form, it is predicted that they gather surrounding materials to increase their mass, leading to the development of complex structures such as rings and channels. These can resemble the grooves of a vinyl record or the spiral arms seen in galaxies like the Milky Way. However, detecting these planetary sculptures has proven to be a challenging endeavor for astronomers. In fact, previous observations had revealed the spiral structure of the protoplanetary disk surrounding HD 135344b, employing the VLT's spectropolarimetric high-contrast exoplanet research, SPHERE, instrument. Unfortunately, evidence pointing to an actual planet responsible for this spiral was not detected at the time. With the capabilities of ERIS, astronomers were able to examine the protoplanetary disk in greater detail, leading to the identification of a potential exoplanet sculpture that could account for the intricate shapes observed in the disk. This promising young planet appears to be located at the base of one of the disk's spiral arms, precisely the area where scientists anticipated such a planet would be found. The significance of this detection lies in the fact that, unlike many earlier observations, we managed to directly capture the signal from the protoplanet, which is still deeply nestled within the disk. This allows us to have a much higher confidence level regarding the planet's presence, as we are observing its own light, Maio elaborated. The results of this research were shared recently in the journal Astronomy and Astrophysics. Feel free to share your thoughts in the comments below. Could this discovery change how we view planet formation? What do you think about the ongoing exploration of exoplanets and their environments? Let's keep the conversation going in our community. Discovering young gas giants, exploring protoplanetary disks. Unveiling the mysteries of a young gas giant and its hidden structures in a protoplanetary disk. The quest to identify planets within protoplanetary disks has proven to be a formidable challenge for astronomers. However, the presence of rings and gaps, often linked to interactions between planets and the surrounding disk, has been observed in nearly every large protoplanetary disk studied at wavelengths of 0.9 to 1.3 mm, provided the spatial resolution is adequate, around 5 astronomical units. An intriguing exception to this trend is the disk surrounding MP-Muse, PDS-66, which, despite its advanced age of approximately 7 to 10 million years, appears to lack these expected substructures. This smooth appearance raises questions, especially since data from the Gaia satellite indicates a significant anomaly in the proper motion of MP-Muse, hinting at the existence of a companion object. In this study, we present high-resolution observations from the Atacama Large Millimeter/Submillimeter Array, ALMA, at 3 mm, which delve deeper into the disk's midplane than previous 1.3 mm observations. These new findings reveal an inner cavity measuring less than 3.0 and a ring located at 10.0. The disk structure, as inferred from these ALMA observations, suggests the presence of a gas giant planet orbiting at a distance of 1 to 3.0. Hydrodynamic simulations support this hypothesis, indicating that such a planet could indeed create the observed cavity. This combination of evidence provides a compelling indirect detection of an exoplanet within a protoplanetary disk, utilizing astrometric data from Gaia. Furthermore, the detection of dust substructures in MP-Muse, made possible by the lower optical depths at longer wavelengths, implies that rings and gaps may be even more prevalent than previously assumed. The challenge of detecting protoplanets. Despite extensive research efforts, protoplanets have been definitively identified in only 2 systems to date, PDS-70 and ERIS 04125+2902. Gaining access to the population of young planets is crucial for enhancing our understanding of planet formation, as it would provide direct benchmarks for our theoretical models. However, traditional detection methods such as transits, radial velocity measurements, or direct imaging are often impractical for embedded companions due to the high levels of dust extinction in the disk and the heightened stellar activity associated with young stars. Instead, the presence of planets is typically inferred through the detection of substructures and velocity perturbations in the disk. The discovery of substructures in protoplanetary disks has been one of the most significant advancements in the field of planet formation over the past decade. Rings, gaps, spiral arms, and azimuthal asymmetries are now recognized as common features in nearly all large disks observed with sufficient angular resolution. These substructures provide a natural explanation for the phenomenon of dust radial drift, where millimeter to centimeter-sized grains interact with the gas in the disk, causing larger grains to drift toward the central star. This process occurs at a much faster rate than the typical timescales for planet formation, leading to a rapid depletion of large grains in disks and presenting a theoretical barrier to the formation of rocky planets and the cause of gas giants. Local gas pressure maxima, which can be induced by planets or other processes, have been proposed as a mechanism to trap large grains, allowing them to grow to larger sizes. However, these hypotheses remain largely theoretical until the advent of high-resolution and sensitive observatories like ALMA and the Spectropolarimetric High-Contrast Exoplanet Research Instrument, SPHERE, which have revealed a wealth of these substructures. The unique case of MP-Muse. Currently, MP-Muse stands out as the only large Class II protoplanetary disk that appears devoid of structure when observed at millimeter wavelengths with high spatial resolution. This K1b star is located approximately 97.9 plus or minus 0.1 parsecs from Earth and has an estimated age of 7 to 10 million years. The dust disk extends to a radius of 45.0 at 1.3 mm, while the gaseous disk, traced by the 12CO, J equals 2-1, line, reaches a radius of 110.0. The ratio of gas to dust radii in MP-Muse is similar to that of structured disks, where dust traps are likely at play. However, The disk appears smooth at 1.3 mm down to scales of 4.0, with only a tentative narrow dust ring detected in the outer regions. In contrast, observations of scattered light from this system indicate a gap between 40.0 and 80.0. The fact that the millimeter disk extends to approximately 55.0, combined with the clear Keplerian rotation of the disk as traced by ALMA and its flat appearance, strongly suggests that the drop in scattered light intensity between 40.0 and 80.0 is due to a shadowing effect rather than an actual gap in the disk. The smooth radial profile at 1.3 mm is particularly puzzling when compared to the typical lifetimes of disks, which are around 3 million years, especially given the age of MP-Muse. To account for the survival of large dust grains in such an old and seemingly structureless disk, several possible explanations have been proposed. 1. Substructures may exist but are obscured by the optically thick 1.3 mm continuum. 2. Smaller substructures below 4.0 may be present but remain unresolved with current observations. Or 3. The disk may genuinely be featureless, with an unknown mechanism retaining millimeter-emitting grains. Gaia's proper motion anomaly. While the 1.3 mm continuum emission from MP-Muse shows no clear signs of planets, its astrometric data deviates from a single star solution. By analyzing the proper motion vector of the photocenter over time, we can identify changes, proper motion anomalies, PMOS, that indicate the presence of companions. PMOS have previously been used to identify exoplanets around main sequence stars, but this method has not yet been applied to sources with protoplanetary disks. Compared to main sequence stars, protostars exhibit additional phenomena, such as variability and strong disk asymmetries, which could potentially induce a PMA. However, analyses of well-known protoplanetary disks suggest that only edge-on, highly asymmetric, or massive disks can induce PMOS, and MP-Muse has a very low accretion rate, making these potential issues unlikely to apply. We determined the PMA of MP-Muse by comparing the proper motion vectors from Gaia data releases 2 and 3. The resulting PMA has a significance of 4.5 sigma, indicating a change in proper motion of delta mu equals 0.21 plus or minus 0.05 MOS year minus 1. By simulating the Gaia observations under the assumption of a two-body system with varying mass ratios and periods, we found that the PMA is most likely due to a companion located at orbital separations of less than 30.0. The absence of astrometric noise further rules out massive bodies with short periods, making the Gaia PMA detection a strong candidate for a companion in MP-Muse. Revealing hidden substructures at 3 mm. To gain deeper insights into MP-Muse, we conducted new ALMA observations at 3 mm, achieving a spatial resolution comparable to the previous 1.3 mm data. Observations at longer wavelengths offer two significant advantages for detecting substructures in disks. The dust opacity decreases with wavelength, allowing us to probe emission closer to the disk midplane, and longer wavelengths trace larger grains that are more effectively trapped in pressure maxima. The 3 mm observations revealed a ring at 10.50 and two gaps at 7.5 and 15.0, which were not detected at shorter wavelengths. The 3 mm image also exhibited flatter central emission, with indications of two peaks suggesting the presence of a barely resolved cavity. By calculating and comparing the intensity radial profiles of the disk at both wavelengths, we confirmed the presence of these structures in the 3 mm image. The discovery of these substructures in MP-Muse suggests that the disk is indeed structured, which could explain both its longevity and the similar gas-to-dust radius ratio observed in other structured disks. While a simplistic interpretation might suggest that multiple planets are responsible for the inner cavity and gaps, we must consider that mechanisms other than planets can also create such features. Moreover, simulations indicate that a single planet can carve multiple gaps in low-viscosity disks, although this may not hold true for models that include radiative effects. Linking observations to simulations. To explore whether a protoplanet within the mass range and orbital separations suggested by the Gaia PMA, massive hidden planet discovered, Giant world 10x Jupiter's size found using revolutionary technique. Imagine a star so young it's still cloaked in cosmic cradle, the kind of place where planets are just starting to take shape. Now picture a hidden world, massive and gas-rich, hiding in plain sight. That's exactly what astronomers stumbled upon while studying a star named MP Muse. But here's where it gets controversial. This planet wasn't just hiding in shadows, it was cleverly camouflaged by the very dust and gas that birthed it. And this is the part most people miss. Scientists only spotted it by combining two cutting-edge tools in a way no one had tried before. Ready to dive into the details? Let's unravel this cosmic mystery step by step. MP Muse, a star barely older than a human teenager, just 7 to 10 million years old, had long been labeled a boring candidate for planet hunting. Early observations with the Atacama Large Millimeter/Submillimeter Array, ALMA, showed a smooth, flat disk of gas and dust, no gaps, no ripples, nothing to hint at hidden worlds. But Dr. Alvaro Ribas, an astronomer from the University of Cambridge, wasn't convinced. A disk of that age should show signs of planet formation, he insisted. So his team went back for a second look, this time using ALMA at a longer wavelength, 3 mm, which pierced deeper into the disk's murky heart. What they found? A cavity near the star and two distant gaps, invisible in previous scans. It was like finding a secret tunnel system in a dusty attic. Meanwhile, across the globe, Miguel Vioque of the European Southern Observatory was puzzling over Gaia data. He noticed MP Muse wasn't sitting still, it was wobbling. At first, he thought it was a mistake. MP Muse was supposed to be featureless, he said. But when he cross-checked with Dr. Ribas's new findings, the pieces clicked, the wobble matched the pattern of a planet tugging on its star. This is textbook planet hunting 101, when a planet orbits a star, its gravity causes the star to sway like a tetherball. But here's the twist, this was the first time Gaia had ever helped uncover a planet still trapped in its birth disk. Talk about a game changer. So what did the math reveal? Computer models suggested a gas giant, 3 to 10 times Jupiter's size, lurking between 1 and 3 astronomical units from its star, that's roughly Earth to Mars's distance. By blending ALMA's deep dive imaging with Gaia's stellar wobble, the team stitched together a compelling case. It's like solving a puzzle with two missing pieces, Dr. Ribas explained. Without both datasets, we'd never have seen this. But here's the debate, if this planet could hide so well, how many others are out there, cloaked in dust? Critics might argue that these tools are just scratching the surface. What if future telescopes, like the upgraded ALMA or the next-gen Very Large Array, InVLA, uncover even more secrets? Could this method revolutionize how we find young planets? Or are we still missing the bigger picture? We'd love to hear your thoughts in the comments. Do you think this discovery changes how we study planetary formation, or is it just the tip of the iceberg? This groundbreaking study, published in Nature Astronomy, opens a new door for astronomers. For the first time, a planet's presence was confirmed indirectly by combining data from ground-based arrays and space-based observatories. It's a reminder that sometimes, the universe hides its best secrets in plain sight, waiting for the right tools and a dash of curiosity to uncover them. Want more cosmic revelations like this? Subscribe to our newsletter for stories that challenge what you know about the stars. And don't forget to explore EarthSnap, our free app, to see how Earth's wonders connect to the cosmos. The universe is full of surprises, let's find them together. Image credit, ALMA, ESO/NAOJ/NRAO/A, Ribas et al. Like what you read? Join our community for exclusive updates and deeper dives into science, space, and Earth's hidden stories.